Hi everyone. This series of videos is going to walk you through the beginning of the next chapter, which is chapter 5, Applications of Integrals. This specific series of videos is actually going to take you through the first lesson, which is definite to integrals as areas. And to access these resources, which you'll need to be able to follow along with the videos, make sure that you open the learning plan. Make sure that you either open and view or print, if possible, the new series of pages that correspond to this lesson so that you can follow along with the problems. I still maintained the structure of our normal packet in the hopes that you could theoretically use this cover page as a notes sheet as you're working through examples and practice problems throughout the chapter. And now that we have information from College Board to suggest that the AP test will be open note, I think compiling notes on these front pages might end up being a really useful tool, because in all likelihood during a 45-minute AP test you're not going to have as much time to look up every individual topic in all the individual pages of a book or an old packet, but having a quick reference source with big ideas might end up being a useful thing. So food for thought for sure. And of course you're not limited to just this one paper, but do keep in mind that if you have access to a printer, printing this packet and using it in the traditional way we use them in class might end up kind of helping your learning overall. In any case, we're going to begin this first video on page 2 of the new packet, and we're going to start kind of reminiscing a little bit about the days when we were still in class talking about the connection between integrals and areas. This section in particular is going to make a little bit more formal that connection and have us practice a bit more of the actual geometry involved in finding an area. We've kind of waffled back and forth. In the previous chapter, we found some geometric areas. We called them Riemann sums. Those were the rectangles. We also found trapezoidal areas in some cases. And then in other problems, we ended up doing it algebraically, either because the area was such a complicated, weird, curvy shape that we couldn't find a geometric area, or because sometimes it was just easier that way. Some problems are just easier to do by doing the actual calculus. The problems that we're going to handle on pages 2 through 5 in this section, though, are often problems for which calculus is just not very realistic. For example, if you peek ahead to page 3, you'll see some kind of crazy piecewise functions with line segments and even a semicircle, so that probably tips you off that in most cases, if you're not given an equation, the algebraic route might not be the most efficient one. You could always write a gigantic piecewise function with all these different parts to it, but that probably sounds tedious, and I'm going to suggest that you avoid that way of thinking, that there's only one way to do an integral and it has to be calculus, because that flexibility, being able to switch on and off your geometry brain versus your calculus brain, is going to really come in handy as we think about this chapter in more depth. Now, as we explore this first topic, definite integrals as areas, I think it's going to be important to get a little bit of context first and to remind yourselves about some of the questions that we were pondering when we were still meeting in in-person classes. This first little section here attempts to kind of theorize some of the big ideas. So if you are kind of interested, or if you feel like you would just need a few moments to read without the distractions, I'm going to suggest that you pause this video and take some time to read through this first half of page 2 to give yourself a bit of context and a bit of grounding. I'll summarize as best I can what this is saying, but again, I do recommend pausing at various points and stopping to kind of chew on the ideas a little bit yourself before you go too far in depth with some of these ideas on your own. Now, the connection that we've made before between area and integral is pretty well established at this point. And we've definitely connected Riemann sums, we've connected straight up geometry, and we've connected antiderivatives in such a way that suggests they're all kind of one and the same. From an actual official calculus standpoint, there's a little bit more to it than just knowing that an integral is an area and that an area is an integral. And this definition in the middle top of page 2 attempts to shed some light on why an integral looks the way it does, why the actual calculus expression with the integral from a to b of f of x dx actually means something specific. We've sort of talked about those expressions as basic notation for an antiderivative. The dx is kind of an implicit notation that told us we were taking a derivative of something in terms of x, and that's the thing that we've normally seen kind of attached as an equation. The integral symbol tells us where the area or the antiderivative begins and ends, but we've always thought of those things as purely symbolic. And in this section, what I hope to do is actually make the connection a bit more clear with some diagrams that represent the real geometry of what's going on. Technically speaking, when you find the area of any section under a curve, whether it's one tiny rectangle or the entire thing from A to B, you're actually finding a real geometric area. So think of what you know about area from probably your most basic pre-algebra classes. You probably didn't even need to learn this from geometry. You've probably heard it since middle school, that the area of something is typically the length of its base times the value of its height. And we're pretty familiar with that area formula, base times height, as the general area of virtually every shape. We think of base times height as a rectangular formula specifically, but pretty much every formula for area kind of boils down to base times height in some way. Triangles, base times height divided by 2. Trapezoids essentially have a base, sum of bases, times a height divided by 2. Everything kind of boils down to base times height when you're talking about area. So keep that formula in mind. When you're looking at this little gray rectangle in the diagram shown here, you can tell that this implied rectangle has a base and a height. If you look at it really carefully, the base appears to be this part that is labeled dx, and the height appears to be this part labeled f of x. So if you think about this quite literally, base times height, you can make, in essence, a substitution. The base of this little rectangle is our dx, and the height of this little rectangle is our f of x. Now you'll notice I took some liberties here with the order in which I wrote things. I technically wrote height first, then base, but we know that when we multiply, you can switch the order and it doesn't matter. So the base dx times the height f of x would give us the area of this little rectangle. Now we know, visually, that this rectangle doesn't quite do a very good job of approximating the whole area all the way from A to B. Obviously that rectangle is a very small sliver, so I need to keep drawing more rectangles and more rectangles and more rectangles to fill in all of this empty space. And once I draw in all of those extra rectangles, whether they're left rectangles or right rectangles, whatever we'd want to use, I know that eventually, by the time this is all said and done, I would have to find the sum of all of those areas to be able to calculate the entire region from A to B. That sum, remember sum begins with the letter S, is where the integral symbol comes from. So an integral quite literally translates as a sum of areas. The symbol itself means sum, and the f of x dx part that you know and love is actually just an area formula. So when you think about this quite literally, an integral is a sum of areas. And that's exactly what we talk about when we talk about that connection between the antiderivative and the area itself. The antiderivative notation that we associate with calculus is really a geometric notation as well. It's a sum of areas, a bunch of base times heights that keep adding up and adding up and adding up and adding up to fill in that whole region. Now, when you're thinking about this idea intuitively, it's not like you have to think about every calculus problem as an area problem, but that's the theory behind it. Just like how every derivative problem is a slope problem, it doesn't mean that in every chain rule problem you're thinking about slopes. It's just that kind of underlying context, that sort of underlying sense of, oh yeah, that's why this works. So this connection isn't really something you have to stew on for a really long time. It's not something that you should obsess over in any major way. It's just something you might want to take a moment to appreciate and to make sure it makes sense intuitively before we continue to build on this idea. Because you'll hear me refer a lot to area when it looks like I'm talking about an antiderivative problem, and it's really because they're one and the same. Now, this would be a good opportunity, if you haven't yet, to really just chew on that idea and to make sure that it makes sense. I'm going to give you a little bit of time between now and the next video to, again, just kind of read over these things to make sure they make sense, and then to start kind of previewing what's down at the bottom of page 2. If you can, try to take this opportunity before starting the next video to explore questions 1 through 5. These are what we call the basic rules of integration, and to see if you can make some symbolic sense of what they mean. There's a little space at the right of each one to try to translate what it's saying into words. So I'm going to challenge you, before I just tell you what the words mean, to really think about these things for yourself in terms of area. For example, if the first one says the integral from a to a of f of x dx, then what would that mean on this diagram? And I'm going to suggest that for numbers 1 through 5, you use the lower diagram, the one that is actually fully filled in, because I think that'll make more sense. But think about intuitively what those expressions would be asking you for. What area are they referring to? If they're saying that you want the integral from a to a, what does that mean? And if you were going to draw a rectangle from A to A, what would that look like? What would its base be? What would its height be? Think on that. And hopefully, once you kind of think about it, what you'll see symbolically will make a little bit of sense. You'll look at something and go, oh, 0. Oh, that makes sense. Yeah, okay, I get where that 0 comes from. So in the next video, I'll explain these in more depth. But before I do, try to challenge yourself a little bit. See if you can figure it out. If you can always check the answer key provided on the learning plan to see if your interpretation is correct before you officially write it down. But definitely take the time to explore this idea a little bit on your own if you can, before I just tell you what to think. Because sometimes those individual explorations can really do a pretty solid job of making an idea our own and helping us take ownership over the idea, rather than just listening to and memorizing all the things that I'm going to say.